This video lecture is on multi-step synthesis, and we're going to go through two examples. Both of the examples are going to start with the same alkene, but we've got very different products. Go ahead and copy down both of these examples, probably on a different sheet of paper. You might need lots of room. And we're going to explore a lot of different avenues to get to these potential products. When you're attacking a multi-step synthesis problem, the first thing that you want to do is look at your functional groups. Here we've got an alkene. What we've learned so far is that alkenes can be transformed into many different functional groups. And so there's a lot of options for this one. And our product is an ether. Thus far, we really only know two ways to make an ether. One of those ways for making an ether comes directly from an alkene. So first looking at this problem, you might think, oh, this is going to be a fairly short synthesis. Well, if we think about how we could potentially make this ether from this alkene, notice we've got the cyclohexane and then two carbons here. Well, that part of the molecule is the same thing as we had in the alkene. And so if we try and think of a reaction that might do this transformation, we can think about using an acid catalyst and then an alcohol. So this will follow the same mechanism that just H+ and water would use. Unfortunately, this is a Markovnikov addition, and so this reaction will form an ether, but not the one we want. Because the oxygen will end up bonded to the more substituted carbon, this would be a good mechanism to go through in practice. The first step of that mechanism, and I won't draw the whole thing, but the first step, as a reminder, would be formation of a carbocation. And so we would get this product. Now, when we look at this carbocation, our initial product here turns out to just be the minor product. Why? Because there's a rearrangement that can occur. Unfortunately, again, this rearrangement doesn't help us get to our intended product ether. We'll get a hydride shift to make a tertiary carbocation. And so the product that would result from this tertiary carbocation would be a different ether. And so for this case, in a one-step reaction, it's not going to do the job to get to our intended product, but we get potentially two other ethers. Mainly, I just went through this for review purposes. So this reaction is not going to work. If it did, this would not be a multi-step problem, it would be a single-step reaction. So now we need to think about the other way to make ethers. If it's not from an alkene using an acid catalyst, then the first thing we should think about, really, is the Williamson ether synthesis. And so the Williamson ether synthesis, especially useful for unsymmetrical ethers, would require an SN2 reaction. Of specifically these two pieces. We want the least substituted alkyl halide, in this case a primary halide, and then whatever alkoxide would do the job. As an aside, you could think of what would be the other combination that could potentially make this ether. And that would be the primary alkoxide reacting with a secondary halide. If these two are to react, however, since we have a secondary halide and a strong base, we would just see an elimination occurring in an E2 fashion instead of the desired SN2 reaction. And so our product would just be this alkene. And you'd protonate the alkoxide to make the alcohol. So these two would not be our intended pieces to use. These two will certainly work in order to make this product. Now, looking at the structure of our starting material, it's evident that this piece must have come from this structure, and this one was just an auxiliary organic alkoxide. And so now we know that we have to get to this structure from here. Perhaps it can happen in one step, or perhaps it'll take more. If you look at this reaction and you can't think of what would work to do that, sometimes you have to use a technique just called brainstorming. And so with alkenes, since we have a lot of different reactions, you might start brainstorming all the ones you know. And don't get too caught up in trying to make this exact product. If you're stuck, just start writing down possibilities. So for example, we know that alkenes can react with HBr. That makes sense. You know, we got to get a bromine on there or a halogen of some kind. Br2, and water. Those all contain bromines. What else can it react with? Well, these can make alcohols easily. We could do hydroboration. Or we can do hydration. And there would be the oxymercuration, or the mercuric acetate, that does Markarnikov hydration as well. Kind of run out of room, but that's another possibility. And there's certainly going to be more reactions that there could be, but this is pretty good for starting our brainstorming activity. And so when you look at this molecule reacting with HBr, that's going to form a carbocation initially at the more substituted piece, but then you'll get that rearrangement occurring that we saw in my first example. And so you would expect with HBr to get this tertiary halide. And so we're, again, far away from this specific primary halide. With Br2, there's no rearrangements that can occur, and we get a bromine out here where we want it, but unfortunately we have another bromine there. This would give us a mixture of enantiomers. So this is closer, but we don't know any reactions that can replace a bromine with a hydrogen. We don't need two bromines, we just need the one. But this is getting us closer to where we need to go. So that's something maybe we wouldn't write off completely going forward. Bromine and water, another example. We can extend this out. Here, bromine goes to the less substituted carbon, and then a hydroxyl group goes to the more substituted carbon. Again, an anti-addition, you'll get a mixture of enantiomers here. But it's kind of the same problem we had up here. We get the bromine where we want it, but then we got some other group on there that we would need to get rid of. We don't have any reactions that just replace these with hydrogens. But at least they're kind of halfway there. In the next reaction, these don't involve bromine at all, but maybe they'll be useful. With hydroboration, it's anti-Markarnikov addition. And so we get a hydrogen here where we need it, but instead of a bromine, we have an alcohol. So that's not going to make this directly. with hydration, again, our major product would be the result of that carbocation rearrangement, the hydride shift, and so we would get an alcohol at that tertiary position. Again, this serves as really good review for alkene reactions. One of these, though, is going to be useful in getting to this product in one step, and it's a reaction we should know. If we place this OH group selectively and in high yield at this primary position where we need a bromine, we know from reactions of alcohols that we can convert that from an OH group into a bromine in one step. And so this can be accomplished with PBr3. PBr3 works great for primary alcohols because it operates by SN2 conditions, so primary sites work the best. For this example, you could also use HBr, and that HBr mechanism would occur through SN2, so it would not allow for rearrangements. This one never allows for rearrangements, so probably your best bet, but HBr would be okay too. So in this three-step sequence, we're able to form specifically this ether. Notice each one of these steps, these are by far the major products that we would observe. And so in many instances, the exclusive product. So a very high-yielding, efficient synthesis in 3 steps. When we look at these structures, it might be best to count our carbons that are not part of the cyclohexane ring. And so over here, we've got 2 carbons in our alkene. In the products, now we have 4 carbons that are attached to the cyclohexane scaffold. What's important to consider is that at some point in this multi-step synthesis, we'll definitely have to add on 2 carbons, probably in the same step. Potentially, it might be 1 carbon at a time if you're just thinking outside of the box, but probably both would be added at the same time since they're part of a chain. This synthesis is going to be more involved. The first thing we should do, again, is look at the products and think about how many different ways can we synthesize specifically that functional group. Here it's just an epoxide. Well, we really only know one route to form epoxides, and that comes from the halohydrin. And so this mixture of enantiomers can form from this mixture of enantiomers of halohydrins. And so the reagent that accomplishes this is simply a strong base. So this is a reaction we know. The base will deprotonate the oxygen of the hydroxyl group, and then that oxygen can just attack from the opposite side in an SN2 type fashion, form a bond here. Notice the stereochemistry of this group, how these two are on the same, they're angled in the same direction because they end up cis in the product. So as this comes over and replaces that bromine, we end up with a cis product. And the same would be true of the enantiomer. It would give us the opposite epoxide. Well, how do we make halohydrins? When we were brainstorming reactions of this alkene, we had a reaction that made a halohydrin. Well, they come from alkenes. And so specifically, thinking about getting to a cis type epoxide, where both groups are angled in the same direction in either case, that must come from a cis alkene. So it's specifically this cis alkene that can create these halohydrins that create the cis epoxides. To do this reaction, and this could be chlorine or bromine, it doesn't matter, we need to react the alkene with bromine in the presence of water. This could give us potentially, since these are both similarly substituted sites, this could give us a mixture where you would have the constitutional isomers as well. Those constitutional isomers, however, would form the same exact epoxides, so there's no stereochemical consequence. In other words, this OH could be over here and the bromine could be over there, and it would still make the same products. And so we would actually get constitutional isomers here as well, where these two positions have switched, bromine and hydroxyl. Now we look at this alkene, and so this is the only pathway we know to get here. So we're honed in here. We've got to go from an alkene to an alkene. If only there was a way to just add 2 carbons onto the end of this alkene. Well, we do not have a way to do that. The only way we can build carbon-carbon bonds from a hydrocarbon starting material is with alkynes. And so we're going to have to go through an alkyne intermediate to get here. Something should jump out at you when you see specifically a cis alkene. It must be cis so that these can be cis. Cis alkenes come from alkynes. So whenever you see a cis alkene, you should think Lindlar's catalyst and hydrogenation. So this is H2 with Lindlar's catalyst, which is palladium on calcium carbonate. There's lead salts involved and quinoline. And that will simply change the alkyne with the same number of carbons. To this alkene, specifically cis. Okay, so now we've got to go from an alkene to an alkyne. In order to make this alkyne, we can first make an alkyne from the alkene in a 2-step sequence, where we brominate or chlorinate. You can use Cl2. This gives us anti-addition of bromines. We would also get the enantiomer. From the dibromide, we can eliminate twice in a dehydrohalogenation using a very strong base, where we need 2 equivalents. The most common one is sodium amide. So with 2 successive eliminations, we end up with the alkyne. Now to go from this alkyne here, we have reactions that involve SN2 chemistry. Again, using a strong base. The first step is to deprotonate or take away this hydrogen to make an acetylide ion that's extremely nucleophilic. To do that, we can use sodium hydride or sodium amide, any base that's stronger than hydroxide, really. And then we need to add a 2-carbon piece on. And this will just be using SN2 chemistry. So we'll use ethyl chloride or ethyl bromide or ethyl iodide. And that will complete the synthesis. For this synthesis, it probably was easier to work backwards because these products must have come from really only one route. Anytime you get stuck in a synthesis, though, it helps to just kind of forget about it and look at your starting material and kind of brainstorm ideas from there. this synthesis depends on alkyne chemistry, but that's certainly not evident in the starting material and the product. It's a much more involved synthesis. Notice every single reaction here is something relevant to this semester's content.